Welcome back to the lecture series of Halliday Resnick Krane Volume 2. In this video lecture, I will discuss MCQ solution of chapter number 33. In this section, I will discuss MCQ solution of question number 8 to question number 12. Question number 8 is a metal slinky can be used as a solenoid. The slinky is stretched slightly and a current is passed through it. Cause the slinky to collapse or to stretch out further. Option A is collapse, option B is stretch out further, option C is neither. The magnetic field is zero outside a solenoid. Or D is the answer depends on the direction of the current. In case of slinky spring as a solenoid, as the current is same in all the direction, so here the coils will attract, then there is possibility that the coils may collapse. If you have not insulated the wires or did not put the ends of the slinky spring such that they are allowed to collapse, then the slinky spring will collapse. So here option A is the correct option. Question number 9 is consider a solenoid with radius is very less than capital L, that is the length of solenoid. The magnetic field at the center of the solenoid is B0. A second solenoid is constructed that has twice the radius, twice the length and carries twice the current as the original solenoid but has the same number of turns per meter. The magnetic field at the center of the second solenoid is, and the options are B0 by 2, B0, 2B0 or 4B0. For this question, we have the solenoid that its radius is very less than the length of the solenoid, and the B0 is the magnetic field that is inside the solenoid. And for such sort of solenoid, it's considered being in ideal solenoid. We have the magnetic field as mu0 Ni, where mu0 is permeability of free space, N is the number of turns per unit length, and I is the current. So let the second solenoid is, we are simply doubling the radius of this solenoid and we are also doubling the length. So it doesn't affect on the value of this magnetic field because we are increasing the length to 2 as well as current to 2I, but the number of turns will remain same. So if we put these value in this formula mu0 Ni, then we will get, as the current is double, so I am writing here 2I, length is double, so I am writing here 2L, so 2 will be cancelled out with 2 and we are getting the same formula. So here option B is the correct option. Question number 10 is how does the magnetic field BZ behave for point Z along the axis of a solenoid with Z is very greater than L, where L is the length of the solenoid, BZ is constant, B varies Z raised to power minus 1, or B varies Z raised to power minus 2, or BZ varies as Z raised to power minus 3. So for this case, you have the situation like this, that this solenoid is along Z axis. Formula to find the magnetic field at this point P would be like this one. So if I just simply lower the point P at the center of the solenoid, then this formula will be mu0 I r square over 2 capital R square plus Z square raised to power 3 by 2. So here you can see that Z square raised to power 3 by 2, 2 will be cancelled out with 2 and you are getting 1 by Z cube. Magnetic field basically varies with the Z raised to power minus 3. The solenoid along the Z axis. So option D is the correct option. Question number 12 is what is integral B dot ds? For the path shown in figure, the options are minus 8 pi multiplied times power minus 7 Tesla meter, minus 4 pi multiplied times power minus 7 Tesla meter, or 8 pi multiplied times power minus 7 Tesla meter, and plus 32 pi multiplied times power minus 7 Tesla meter. To solve the B dot ds closed integral according to Ampere's law, first of all we have to check the direction of this impedance loop. So you can see here it's actually anti-clockwise. So all of the currents that are outward of the direction, they are basically taken as positive, while all of the current that are inward to the paper, they are taken as negative. Because in case of outward current, you can see here the direction of magnetic field is anti-clockwise. That's why current of 1 ampere and 2 ampere is taken as positive, while the direction of this current would be inward, the 5 ampere, so it would be taken as negative, because the direction of magnetic field due to this current is opposite to the direction of the impedance loop. That's why I have taken here 1 ampere and 2 ampere as positive and 5 ampere as negative current. So here you are using the formula B dot ds closed integral is equal to mu0 I. The value of mu0 is 4 pi multiplied times power minus 7 Tesla meter per ampere, where the current is basically total current. Here you can see other currents 3 ampere and 4 ampere as well, but these currents are outside the impedance loop. That's why we are not including 4 ampere and 3 ampere. We are only considering these currents like 1 ampere, 5 ampere and 2 ampere. So as I have already told you that 1 ampere and 2 ampere is taken as positive, while 5 ampere is taken as negative. So 213 amperes minus 5 ampere, you get minus 2 ampere. That would be multiplied by 4, then you get minus 2 multiplied 4 is a minus 8, pi multiplied times by minus 7 Tesla meter. Ampere will be cancelled out with this one. So option A would be the correct option.